Good afternoon, everyone. So I'm Nikhil. I work as a machine learning engineer at H2O. So what I'm going to present today is how H2O leverages power systems to run things faster. So first, how many of you guys know about H2O, the company?
Wait, I just heard.
Okay, not many. So maybe this will be helpful. So H2O is one of the startups in the machine learning field. So we have multiple products, mostly open source, except for a couple of them. So a few open source products are the H2O3 itself, which is something like Spark, but it's way more efficient when you go about modeling. And then we have sparkling water. So in sparkling water we connect Spark and H2O. So basically you use Spark to run your ETL, and then you model in the backend using the H2O libraries. Then we have something called H2O4 GPU, which is the machine learning libraries which run on GPUs, which are way faster than the CPU models. So H2O3, the first one there is runs only on CPUs, not on GPUs. And then I work on Driverless AI, which is a closed source product. So this basically automates the machine learning life cycle, like the demo which we saw before. So the machine learning life cycle consists of doing an EDA and then creating your model first, a baseline model, and then iterating, and then you reach your final model. So Driverless AI aims at automating that part of it. So yeah, so now on the talk would be mostly about Driverless AI. So Driverless AI is an automatic machine learning platform that delivers advanced functionalities, which has data visualization, feature engineering, and it has model interpretability. So we'll see a demo of it as well. So we'll understand each of those points like data visualization, feature engineering, model interpretability in detail when we go through the demo. These are the key features which mostly list the same thing which was in the slides before. So I'm just running through the slides so that we can spend more time on the demo rather than the slides. So this is the Driverless AI architecture, wherein the major focus is on this part, which consists of feature engineering, which becomes very tedious and very time consuming when you try modeling, and the feature engineering for a tabular data is different from a time series data and for NLP problems and deep learning. So Driverless AI takes care of all four scenarios, like the tabular data and the registry. So, and then you have the Driverless AI server itself, which runs and basically the feature engineering part is ingested into the Driverless AI engine, and it runs on GPUs or on CPUs depending on what hardware you have. And then there is some visualizations, auto visualization, where you just feed in data and then it tells you what are the data points or the columns or the row fields which you should be looking into, which are outliers or are special in some sense. And this basically deals with the real-time deployment of Driverless AI, like how do you score? You can score by using HTTP connections or thread servers, or just via Python, or deploy using Java objects using modules and pojos, which we have for Driverless AI. So these are basically the artifacts which you use in real time for scoring. And this is the main engine which runs the genetic algorithm where all the transformations and the data is fed in. Does it make some sense?
No.
Okay. Yeah, so H2O integrated with Power. The integration started like a year back. So Driverless AI was predominantly running on Linux, which was Red Hat and Ubuntu. So we started integrating, basically compiling driverless AI for power machines. So this started 1 year ago. The libraries which driverless AI were using, like the packages, were limited in distribution of dependencies, so we had to compile them for power machines. And then there were compiler differences which driverless AI was using on a native Red Hat install compared to the power machine. So those things needed to be plugged in so that driverless AI can run on a power machine. And now we have an RPM and a dev packages for driverless AI on power. We have Docker image, and you can also use driverless AI on the IBM cloud private. So most of the packaging work was done by one of our developers named Patrick Rice. So I borrowed a couple of slides of his, which he gave from his talk yesterday at H2O World London. So he basically worked on compiling TensorFlow for power, so that driverless AI can in turn use TensorFlow, and then I think it was deployed in TensorFlow 1.11.0 and CUDA 9.0. So with this compilation, driverless AI can run on power machines with GPU support, and it works out of the box now. So yeah, I'll go through a demo. This would be an interesting part, not so much over the slides. So how many of you have taken a course on machine learning or solved a machine learning problem, as such, like taking the data and create a model and then score it? A few of you. So driverless AI basically automates the entire machine learning flow. So you give driverless AI tabular data, and it will give you a model which will work very fairly well and impartially on the new test data set which you would have. So the first step for any machine learning product would be to ingest the data. So we have various connectors through which we can bring in the data into driverless AI. If I click on add data set, you see a list of drop downs. So yeah, I'll just read out a few. The first is the file system, which is the local file system. Upload file would be from like my laptop and not the EC2 machine. So EC2 machine is a local file system, and the upload file I can use the upload file to ingest the data from my machine, which is this Mac. And then you can pull in data from Hadoop, Amazon S3, Google Cloud Storage, Google BigQuery, Minio, Snowflake, and there are a few more which are not activated here, like the KDB database, and you can even put in a Hive query to pull the data. So these are the various ways by which you can pull in the data into the product. So once you have the data, it shows up like this. So this is the credit card train data. So it's 2 MB in size. It has 24,000 rows and 25 columns. So now we can either look at the details of the data set, or we can visualize it or predict it. So we'll go one by one to each of these. So if I click on details, it will tell me the metadata about the columns and the rows in the data set. So like it says that the first column is the ID, and it tells me the type, which is int. The count is 24,000 hours, and the mean, and it shows some statistics about this column, like the min, max, standard deviation, frequency, and how many unique values are there. Since it's an ID, all the values are unique. If we go to the second column, it's called limit balance. So that's again int, and it shows the statistics about the column. Similarly, we have the statistics and the distribution graph for each of the columns, and this is the label which we want to predict. So it says whether the user will default the payment, or will he not default. So this is a Boolean type, which says whether he'll default or he'll not. So it's a yes or a no. And if you want to see the first few rows, first 23 rows of the dataset, you can just click on dataset rows and it will show you the first 23 rows. I don't know if it's visible, but you can trust me that there are it's showing 23 rows. It's like a head of the file. And now if we go back, we can do a visualize. So visualize will give you the interest, will actually point you to the columns and the rows which are interesting, and it won't show the visualization for each and every column. Like if some columns are statistically sound, it won't even show the visualization for those columns. Only if it's of interest, it will show those. So these are the graphs. For instance, there is the outlier plot. So if I click on the outlier plot, it shows me like the column bill amount 4. This has some outliers. The red dots denote the outliers. So if I click on a red dot, it shows me the row to which it corresponds to. So it's an outlier because of some reason in the data. Maybe the bill amounts are too high. That's what I can infer looking at this. And if I scroll right, it shows the outliers in bill amount 3, and then if I click on this, it shows me the outlier rows. And sometimes the outliers would comprise of multiple rows. So basically that would mean that those 2 rows are outliers for the same reason. So this is one of the graphs. Then an interesting one is the parallel coordinate plot. So this basically plots the rows of the dataset which are interesting. So this is the highlighted one is one of the rows. So for this row the limit balance is 0. The payment amount is somewhere I don't know what, but it gives you a general trend of what each column value is for this particular row in the original dataset. So you can highlight one of these and then you can see what's the value of each of the columns. Basically get an idea whether it's a high value or a low value. So all the lines, the connected lines show outliers from the original dataset, and you can looking at it you can reason out why it was an outlier. So it helps you to understand your data well, and then the most popular heat map is there, so it tells you, it gives you a heat map for all the columns in the dataset. And then radar plot is something similar to the parallel coordinate plot. So it's just a polar way of representing the same parallel coordinate plot. So if you highlight one, it will show you the values for each of the columns for a row which was an outlier or an exemplar. So this is the first part of the product, which is called AutoWiz. So this was architected and developed by Leland Wilkinson, who is a professor at UIC, who is a part-time professor at UIC and works for H2O like full-time. And I'm going back to the data set. So the second thing is predict. So this is where the main experiment runs, where the machine learning model is being built, and so the machine learning model just gets in the data set and then it will build the model. So it makes use of genetic algorithm into which the data set and the transformers are fed in. So here we are using the credit card train in the same data set, and I need to tell the driverless AI which is the target column. So that's the default payment column. So these 3 are the metrics: accuracy, time, and interpretability. So oops, is it visible? Somewhat. Very light. Okay, so I'll read it out. So the accuracy, if you look here, so it says here accuracy below this. So you can turn the knob and increase it till 10. So it basically tells the driverless AI to build a model which is very accurate. But if the model is very accurate, it might not be interpretable well. So companies like financial companies would not want a very accurate model, but which cannot be interpreted. Rather than they would like to have a model which is more interpretable, but maybe they're okay with a little lesser accuracy. So that's what the first law talks about. And then the second one is time, like how long do you want driverless AI to train your model. So depending on what you choose here, the training time can range from a few minutes to a few days to a few weeks. And then the third one is interpretability. So this tells you how interpretable you want the model to be. Like if this is turned all the way to 10, it will just create a tree model. It won't create a boosted model or a deep learning model in the hindsight. So after I have selected the accuracy, time, and the interpretability. One second. So once I have selected all these three, I can just click on launch experiment and it will start creating the models and running the genetic algorithm. So genetic algorithm will take in the transformers and figure out like what's the best transformers for each of the columns, apply it, and then give you a model at the end of the training process. So and if the machine has GPUs, it automatically picks up the GPU, and the default since it's a classification problem, the default metric for scoring is AUC. You can change it to one of these, and then you can train your model depending on what you want. So I just click on launch experiment, and it will start running the genetic algorithm. So this can take some time, but if I click on, so it keeps giving me notification from time to time, like the first notification which it's showing here, it says like the column was ID, the first column was ID, so it's dropping it and won't be using it for creating models. And there are these graphs which so these are the graphs which a data scientist always makes use of while creating models. So the first is an ROC curve which shows the accuracy. So this accuracy, it gets the data live as it's training. So if the training will progress, the accuracy will increase or decrease depending on whether the model being created by Driverless AI is good or bad. And then you can always go and check the precision recall curve and the lift, the gain, and then the GPU usage. So the machine on which this is running has it should ideally have had 8 GPUs, but it shows only 4. Maybe the other 4 are busy with running something else. So this shows like how busy the GPUs are, and the above here it shows like the CPU. The first row is the CPU usage. The second one is the memory usage, like the RAM usage. So it's running the experiment, and at the end of it will have a model which will have fairly high accuracy. And you cannot see it here, but it says here that it's used an light GBM model till now, but here it's saying that now it's using an XGBoost model. So Driverless AI can use multiple of these models, and at the end it stacks it to create the final model. So we use light GBM, XGBoost, TensorFlow, and a few more packages to build the model. So this can take a while. So I'll move out of it. I'll show you an experiment which I already finished running. So on the same data set. If you look at this experiment, it says that it ran for 54 minutes, and then it has an accuracy of of 78.5, AUC of 78.5, and then I turned one of those three knobs and to change the accuracy to 6, the time to 4, and interpretability to 6. And this model ran for 8 minutes, and it has a similar accuracy, say 78.2. So, but if you see, the model which was created here was a 411 MB model, but the one on top here it's a 352 MB model. So when you do a real-time scoring, you'll have to use the model which is being listed here. So you'll have to deal with a 400 MB model or a 352 odd model. Yeah. So that's the second part of the driverless AI, and the third part is the MLI, where we actually try understanding the model which was created by driverless AI. So if I click on one of these models, so I clicked on a model which finished running. So I'm just waiting for it to load. Yeah. It's taking time to load because of the network latency. This thing is running on an EC2 machine. And this is just a UI issue. It should just show me the finished status and not a running status. So that should come in like a couple of seconds. So this says interpret this model. So whatever the final model was created by driverless AI, which has an accuracy of 78.54, we want to see if this model can be put into production or not, or whether we can reason out for a particular customer if he'll default or not. Like, can we give him a written statement like why do we think that you will be defaulting? So I just clicked on interpret this model. So it runs the H2O, the open source H2O3 now, and then it shows a few graphs. It will show a few graphs by looking at which we can figure out what was the reason for a particular row in the data set that the customer will default or not. So I'll just jump to the dashboard. So we make use of a few techniques to reason out the logic. So one is the line, which is pretty famous, and the feature importance. The second is we look at feature importance. So feature importance comes from the GBM models which was created, and how do I scroll down?
You have it down.
1 second. No, I just cannot find the scroller. Yeah, it's outside. I'm just waiting for the page to load. I'm using my mobile. Yeah, so currently the laptop is using my mobile Wi-Fi, which may not be so good. Okay, I have this back. Yeah, I cannot find a scroller, but if you look here, it's a decision tree, so we can. So the model which was created by driverless AI might be a stacked model of like 1,000 different models, but if you want to reason out the final predictions, so that's done by using a surrogate model which tries to mimic the same predictive value as a stacked model. So this is so the decision tree being created here is a surrogate model which we are using. So this will give you the same prediction as the stack model, but here you will be able to reason out way more easier. Like the first dot say represents the base zero. So if the base zero is less than 0.0794, then you go in this direction or you go in this direction. So a financial company can actually give the reason for telling a customer whether it default next or not in writing using this model, which is a surrogate model. And then we use something called partial dependency plot to just reason out and make your analogies or the statement more concrete. So these are the four models which we use to reason out the complicated model which was created by Driverless AI using the genetic algorithm. So yeah, so that's more or less about the demo. Do you guys have any questions on this? Yeah.
So is the GA being applied to evaluate which model is working video stacking, or is the GA being applied by the data set?
No, so that you're talking about the product itself, right?
In driverless AI,
Yes.
you are using a genetic algorithm.
Yes.
The fitness function.
Yes.
Fitness function is the predictor for it.
Yes.
And is the GA being applied to evaluate which model is doing well, or is the GA being applied
No.
to build the model?
No, so we feed in the data. So the genetic algorithm makes use of the transformers which we have built in there. So genetic algorithm decides which transformers to use on each of the columns and then creates the new data set. Like the original data set had 25 columns, a new data set might have like 25,000 columns. So genetic algorithm decides what features should be created, and then on those features the final model is being built. So and the final model is a stack model, which would be a stack model of like various like GBM with multiple parameters, XGBoost with multiple parameters, and so on.
So your GA is doing some kind of feature engineering.
Yes, so GA is genetic algorithm is basically doing feature engineering. Any more questions?
Does the GA leverage GPU for this?
Yes. The entire thing runs on GPU. Like if I go to the experiments page, and when it was actually running, the spinner was running, so you can actually see whether the GPUs are being used or not, like at the bottom here.
Yeah, I saw it.
Yeah, so there you see like how many GPUs are used by this experiment, and the spikes there basically tells whether GPU is being used or not. So the genetic algorithm in that driverless AI runs on GPUs. Essentially, if the GPUs are there, if not, it will fall back to the CPU mode. Any more questions?
You showed that interpretability now and everything.
Yes.
So how does the user select what the right interpretability factor is? How does it map to the end business requirement?
Yes. Yes. So yeah. So that comes from practice. Like as a guideline, if you give an interpretability as 1, then it will create the most complicated model, which would be very difficult to reason out. But in the knob, if you go to 10 and then select 10, then it would create almost a decision tree, which is like highly interpretable. You can tell the model is highly interpretable, so you can actually tell what's happening for each row in the test data set. So when you use driverless AI, it's up to the business, like what kind of threshold do they want? Do they just want low accuracy but a high? It's again like what do you call it? What the business owners want. So if you choose one, it will create a very complicated model. If you choose 10, it will create a simple model. The simple model is very easy to interpret, but not the one if you choose a knob. If you turn the knob to 1. So where the risk factor lies for a particular company, the company needs to decide. But it's like 1 is the most complicated one, 10 is like the most simplest model. Does it answer your question? Any more questions?
Hello sir, what we understood that H2O is using its own defined library to process the data, right?
Sorry, can you come again?
Yeah, what we understood basically that H2O has its pre-defined libraries from which it takes data from the various web APIs and processes to the according to user's need, right?
No, so you feed in, you have a data set, you have a machine learning problem, so you have a data set for that. So you feed that data set into Driverless AI and it will do the feature engineering and the modeling part of it and will give you a final model with a score and various means to deploy the model.
Okay. So can we say that H2O itself is learning, it's updating its libraries by the data it processes?
So it's not actually a library. It's like the genetic algorithm code which runs. It makes use of the data which you feed in to create better features and then creates a model on top of it. So basically the demo, not the demo, the notebook which we saw before. So that went through the entire steps of a machine learning modeling project or an assignment. So the entire flow from beginning till the end, that's automated by Driverless AI. Does that answer your question?
To some extent.
So what's the remaining part?
Like the remaining part is that does user also contribute to make the H2O systems efficient? Because we are feeding data on the various parameters. So by using regulation methods, H2O itself it's sharpening its own skills.
No, so you get an install of the Driverless AI. So you install it on your system, you use it locally or on cloud, and it's your data which goes into the Driverless AI system, and you use the outcome of it. None of this gets transmitted to the H2O library as such. It's like once you buy it, it's yours. So whatever you run, it's just accessible to you. It doesn't, nothing out of this system goes back to H2O as such.
Okay.
So it's not making itself intelligent by running on your data.
Okay.
So intelligence is being added by the data scientists at H2O. So they have got recipes, and in the first few slides where the architecture of Driverless AI was there, I pointed out that there are recipes for tabular data, NLP data, time series data, and some deep learning models. So those are the recipes, those are the brains behind H2O, and it's not actually learning or evolving based on the data you are feeding into it. Yeah, any more questions? Oh, sure, okay. Thanks everyone.